This is the short summary for Chapter 4. The main focus is functors, to explain motivation, the laws, and the structure of functors. I begin by saying that we want to describe the properties of data containers, such as sequence. We want to generalize and formalize the properties of such containers. And I show that the main idea of doing this is to talk about how containers allow us to manipulate items held in them by applying functions to those values that are held in containers. And this manipulation is performed using the function map, which changes one container into another by applying a function. I give an example of option as a very simple container. I explain how we can understand that as a container and how the map function works. And I motivate the laws of the functor by saying that we would like to avoid information loss and we would like to actually manipulate values rather than do nothing, say. Here is how these requirements are formalized. We want to say that information loss should be avoided when the map of identity is identity, and I give an example of when this is not the case. Also, I introduce my short notation for code. This is not standard at all, but this is convenient for proofs. Now, I explain that fmap is more convenient for reasoning about the properties of functions, and I motivate the properties, the identity law and the composition law of fmap, which is, these are two laws. This gives me a way to define what a functor is. It's a generalization of container that satisfies our requirements, does not lose information, and allows us to manipulate data in the container. I verify that the laws hold by looking explicitly at code for the option. I give many more examples of functors. These are all functors in the standard library. And I also explain why set and map are not quite functors, or almost, but not quite exactly functors. I show test code for that. More examples are polynomial type constructors that are made from products and disjunctions. I give examples for that. Also, it's important to find out what are type constructors that cannot be made into functors. So what are not functors? Well, this is one example. This cannot be made a functor because it cannot have a map function. Another example is this. I explain why that works, or rather does not work for functor. More non-examples are containers that could be functors except that map is incorrectly implemented. So I show what to avoid when implementing the map function. I also give an example of a recursive type and how to implement the map function for it. So in all these examples there is code that shows how that works. Now in certain cases the type constructor has this shape and it's not a functor, but it has a different function called contramap that is very similar in type signature but has a reversed error. So those are called contrafunctors. I explain the interpretation of contrafunctors. Functors are containers with data, they contain data. Contrafunctors consume data, they're consumers of data. And I show that this example is actually neither a functor nor a contrafunctor. And I explain the connection between functors and contrafunctors and subtyping, or covariance and contravariance and subtyping. This connection is usually made mysterious in programming language books. In fact, there is a very direct connection. Covariant types are functors and contravariant are contrafunctors. And I explain why that is so. In these worked examples, I show different type constructors, which are functors or contrafunctors, and I show in detail how to implement the map or contramap function for them. And I give exercises that are similar to those worked examples. Another interesting question is how to recognize if something is a functor or not. So if I give you a type expression like this, now this is in short notation. Translated into code, this will be a lot of code, so it will be not easy to see necessarily. I give a way of finding out. And so, in fact, I show how larger type expressions can be built out of smaller ones using certain constructions or operations. And so I also show why all polynomial type constructors are functors. In other words, if you do not have the function type, if you only have these constructions, then you'll always end up with functors. And I go through each of those constructions and verify the laws. So if laws of the functor hold for these two, then they will hold for this, and so on. Once we have verified all these laws, it is unnecessary to make any proofs about functor laws. It is just required to check that an expression is obtained through these constructions, and that's sufficient. The laws will hold. So for instance, for this expression, we just verify that the type parameter A is always in covariant positions, and that this entire type expression is made out of parts with the constructions that we list. And since we have proved each of these constructions in detail, that's sufficient. So the proofs I show as worked examples how to prove the functor laws for each construction, for the disjunction construction and for the implication or function type construction. And in the exercises, I ask you to derive some more laws for the remaining constructions.